Hi guys, here in this video we are analyzing Telangana Set 2017 Chemical Sciences. Watch the video completely to get detailed conceptual analysis. Okay, just look at the given problem. Which of the following molecules or species cannot be studied by electron paramagnetic resonance spectroscopy? Okay, here we have given with EPR spectroscopy. In its name, we have paramagnetic. So, whenever a species or molecule has unpaired electrons, then the species or molecule is EPR active. And we can study EPR spectra on those molecules or species. Okay, right. Now just look at the given species and molecules. We have nickel complex or nickel carbonyl, nickel tetracarbonyl, where nickel is in zero oxidation state because CO is a neutral ligand. Okay, in that case we have D8 and the S2, but CO is a strong field ligand. Okay, that's why two electrons are paired up in d orbital. In that case it contains d10 electrons. Okay, so from this we can say that there are no unpaired electrons in nickel tetracarbonyl, and that's why which is EPR inactive. Okay, right. Now just look at the second, that is vanadium complex, where we have acetyl aceto ligand. Okay, acetyl acetonate, so ACAC2, so which is a bidentate ligand. Just try to draw its structure. So it is just like here, square pyramidal like structure, and the vanadium is in +5 oxidation state, so it has 0 electrons in its valency shell. That's why it is also EPR inactive. Now just look at the third one. We have one radical on the carbon, so it is EPR active. Whereas if you look at the fourth one, in that nickel complex, simply we have nickel is in +2 oxidation state. It contains 8 electrons in its d orbital, and you can see chlorine is a weak field ligand. That's why we can observe 2 unpaired electrons in nickel +2 complex. So whenever we observe unpaired electrons, it is EPR active. So C and D are EPR active, A and B are EPR inactive. That means we cannot study electron paramagnetic resonance spectra of a nickel carbonyl and vanadium complex. Okay, next question. So just look at, we have given with, consider the picture showing the rifle target by a contestant. Okay, just observe it. How would you describe the shooting of the contestant? So just observe here, we have all so targeted here, and this is the center of the target. So here we can say that it is inaccurate but precise. Okay, so whenever we call it as accurate, if the target hitted here at the center, then we call it as accurate. But it is precise because it is not accurate but precise because all the bullets are near. Okay, so option B, inaccurate and precise, is the correct option for the given problem. And next question, so just observe, why does absorption spectrum of given aqueous titanium complex, where titanium is in +3 oxidation state, exhibit a broad band with a shoulder? Okay, so the reason is the excited state of titanium complex undergoes a John Teller distortion. Here option C is the correct answer. Now just try to look at the given titanium aqueous complex, where titanium is in +3 oxidation state because water is a neutral ligand. Okay, in that case titanium has only 1 electron in its d orbital, and in the presence of water ligands the degenerate d orbital splits into T2G and Ag. So 1 electron is present in its ground state T2G. Okay, right. We know that John Taylor distortion is maximum whenever the unsymmetrical filling of electrons are observed in Ag level. Okay, so whenever we compare with T2G, that's why John Taylor distortion is very small when we observed electron in its ground state, that is in T2G of given titanium aqueous complex. But in its excited state, electron excites to EG level, and where maximum or sizable Jahn-Teller distortion is observed. Okay, so in that case, EG further splits into electronic energy levels as A1G and here B1G. Okay, so just due to that splitting or Jahn-Teller distortion, and here we can observe a shoulder with broad band. Okay, right. And here other possibility or other reason is we can see possible spin allowed transition, that is there is no sign change you can observe. Okay, plus half, it just moving as plus half, that's why delta S is equals to 0. So here due to possible spin selection rule and Jahn-Teller distortion in excited state of the given titanium plus 3 complex aqueous complex, it is showing broad band with a shoulder. And we can also observe vibronic coupling here in this given complex. Okay, right. And here the same kind of question is given in CSIR net June in chemical sciences. Okay, so here we can use this concept on that. Now next question, the fourth one, what is the order of energies of 4s, 4p, 4d and 4f orbitals of hydrogen atom? So simply we know that the energy of hydrogen atom is simply directly proportional to n square or proportional to 1 by n square. That means simply energy of hydrogen atom is related to principal quantum number only. Now in the given problem we have 4s, 4p, 4d and 4f. That means all the principal quantum numbers are same. That's why that means the energy of all the given orbitals must be same or must be equal. That's why fourth option, that is D, is the correct answer for the given problem. Okay, now next question, fifth one, the least energy state term symbol for the nitrogen atom is. Now just try to take the electronic configuration of nitrogen atom. So here 1s2, 2s2 and 2p3. Okay, that means we need to consider p orbital here, 3 electrons are present and then L value equals to 0 for it. So it indicating that here yes term. Okay, now we have 3 unpaired electrons, then S is equal to n by 2, here number of unpaired electrons, so 3 by 2 here. Now multiplicity, that is 2s plus 1, 2 into 3 by 2 plus 1 equals to 4. Now it is S4. Now J value is calculated as L plus S to L minus S. So here L value equals to simply 0 and S value equals to 3 by 2. Now just take simply 3 by 2 here. So completely the term symbol is yes, 3 by 2, 4. So option 3 is the correct answer for the given problem. Okay, now just look at the next question. Whereas a charge transfer band refers to a spin forbidden transition, a ligand to metal or metal to ligand transition, Laporte forbidden transition observed due to molecular distortion, a DD transition. The correct answer is ligand to metal or metal to ligand transition, because here charge transfer transitions are spin allowed, okay, spin allowed and Laporte allowed. Okay, so from this information, so we can simply eliminate all the three options and second option is the correct answer for the given problem. And next one, the following, just look at here, the following spectral data is available for nickel complexes. Observe it, we have different spectral values are given. Two very weak bands are observed. What is the magnitude of crystal field splitting? Here the given nickel complex, nickel is in +2 oxidation state, which contains 8 electrons in its d orbital. So that for d8 electrons, V1 is the magnitude of crystal field splitting. Okay, V1 equals to delta 0. So here V1 should be 10,700 and that's why here A is the correct answer for the given problem. Okay, right. If you are interested, just visit and join on CHEMMasters.online, the best online courses, or just download mobile app CHEMMasters from Google Play Stores and join online best online courses to get guaranteed success. Thank you very much.